Hello, welcome back. So we are continuing our discussion of greatest common divisors. Definition 2.12 said that the GCD, that's the notation, of two integers a and b is the largest integer d that is a common divisor. Okay, so that means the largest d such that d divides both a and b. Makes perfect sense based off the name. The greatest common divisor is the largest thing which is a common divisor. Now, here, theorem 2.13 is a pretty interesting theorem. It's known as Bézout's identity after Etienne Bézout, who is a old French mathematician. I don't think he had a lot of claims to fame, but this is certainly one of them. Okay, so here's what it says. If a and b are positive integers, then there exist integers k and l such that, so here's the conclusion, that the GCD of a and b, okay, so think about two numbers, 2 and 6, the GCD of 2 and 6 is 2, can always be written as a times some k plus b times some l. That's interesting. So every time you have a GCD, if you just write GCD of a and b, it's just this sort of mysterious thing, right? I mean, you have two things inside of a function. This is kind of like f of x, but it's instead of f, you have GCD, and instead of x, you have two variables inside. But it's just sort of like a black box, right? There's nothing you can say much about it. It's just the GCD. That's all it is. What Bézout's identity allows you to do is to write this mysterious function in a very concrete way. Or if it's, I said 2 and 6, right? This would be 2k plus 6l. So there's some k and l for which whatever the GCD equals, you could always express it as in this sort of way, where you have, and this is good. I mean, this is linear, right? You have a linear term and added to another linear term. So anyways, this is a very, very nice expression of a mysterious GCD. But let's actually do some examples to show you. So I thought I'd ask my phone to give me some numbers between 1 and 20, and we'll use those in our scratch work to sort of understand what's going on. Give me a number between 1 and 20.
A random number between 1 and 20 is 8.
8, okay, so that's the first one. So let's make sure we understand this by doing some examples. I would always recommend this. Okay, so let's do an example. A equals 8, and give me a random number between 1 and 20. Okay, didn't say it. There you go, I'm covering up my daughter's face. 9. Okay, this is not the best one, but nevertheless, let's do this one. 9, okay. So what is the GCD of 8 and 9? 1. Okay, that's why I said it wasn't the best one, because the GCD is a simple number, but that's fine. Okay, so let's show how it works in this case. So this claims that I can write 1 as 8 times some k plus 9 times some l. Do you see a way to do it? Keeping in mind that k and l are any integers, including negatives. Yeah, so 1 is 8 times negative 1 plus 9 times 1. Okay, so not the most interesting example, but nevertheless, it worked. So two numbers, I was able to find it. Let me get another GCD. Give me a random number between 1 and 20. 1, it told me 1. Give me a random number between 1 and 20. 12. Okay, let's do 12. So we have, so let's switch out b for 12. So if a equals 8 and b equals 12, okay? So let's see, what is the GCD of 8 and 12? That'll be 4, right? So can we write 4 as a linear combination of 8 and 12? And the answer is yes. 4, does 4 equal 8 times k plus 12 times l for some k and l? Do you see the way to do it? I can't believe it's -1 and 1 again. That doesn't always happen. Let's just... So you can see how to do it, right? This would be -1 and that'd be 1. Let's make it a little bit more interesting. Let's just have it be 4 and 12. The GCD is still 4, but how do we make it now? 4K plus 12L. Well, actually, some of you might have different answers than others. So one way is you could now just double K. So 4 equals 4 times 2 plus 12 times -1. Or you could also say 4 equals 4 times 1 plus 12 times 0. Okay, you can just cancel out that second term. And if I gave you some time, you could come up with many other ways. There are, in fact, infinitely many. Interesting fact. Okay, so there you go. Hopefully that made some sense. And with that, let's discuss how we might try to prove Bézout's identity. So I'll say up front, this is a challenging proof. It's much longer than our previous proofs. And in the following section, section 2.5, we're going to see even more challenging proofs. So that's in part on purpose. So, I'll say only in part though. So this content, the content in this section, not in the next section, it's good to include it earlier on in this book because the content can then be used in further studying other types of proof techniques. So it's good to have it earlier. Also, especially the next section, it's a little challenging. And so you get it early, and then throughout the course, you get many reps in wrestling with that concept. And then by the end, you have a better grasp of it, which is good because it's going to be an important concept in many other courses that you're going to take. Also, as long as you preface this by saying, keep in mind what is to come is going to be one of the harder proofs in this entire book, then that's a good thing because then you can say, okay, let me challenge myself. You know, if you don't follow along, if you get lost in the argument, don't worry. That's not a bad sign. It's not like everything from this point on is going to be that hard or harder. No, it's gonna be a challenging moment, and then we're gonna move on and starting with chapter 3, things are gonna get a little lighter again. But anyways, so think about this as being a real challenge moment. See if you can understand this entire argument, this entire proof. But if you can't, as many of you won't be able to probably, don't feel discouraged. That's perfectly okay. I'm sure a lot of professors would just skip the proof that I'm about to give you, which would be a very reasonable decision. But I'll show it to you because some of you might be interested. Okay, so how might we try to prove something like this? Seems a bit of a challenge, right? I mean, if you thought about this for many hours, you might not come up with a way to do it. I might think about it if I didn't know the proof, might think about it for many hours and not come up with a way to do it. It is actually challenging, okay? It's very challenging. But here's how we're going to prove it. So here's my start of the outline. So first is, these steps are not going to be made equal. The first step is simply setting up the problem. So A and B are positive integers. It might be easy to think about these as like variables, like they're moving around. We don't want that. Let's think about fixed positive integers A and B. So that's step one. Assume A and B are fixed positive integers. Now I'm not assuming anything about them beyond that they're fixed. So no matter which two positive integers you want, the proof is going to go through. I'm not like assuming they are fixed positive integers and they are 3 and 7. No, I'm not going to do that. Any two positive integers the proof is going to apply to because they're totally arbitrary. But they are fixed. So assume A and B are fixed positive integers, which also fixes their GCD. So since they're fixed, GCD of A and B is also fixed. We don't know what it is, but it's fixed. Okay? Step 2 in our proof is going to be to find some K and L which work. Okay? So this is the step that requires a good idea. The person who came up with this, I assume it was Bézout. I guess I haven't looked into the history. The person who came up with this clearly played around a lot with examples. They clearly had a very good grasp about why this thing is true and the way forward to try to prove it. So there's a cleverness in this second step. Maybe not even cleverness. Maybe that's not the right word. An insight. There's a deep insight in that step. Step 3 is going to be to show that the GCD of A and B does indeed equal, that it does work, plus BL, so that's true, by using the definition of GCD. So what do I mean by that? Well, step A, so we're going to show both that it's that this number, AK plus BL, that's a fixed number now, right? Because we fixed A and B here, and in step 2, we actually found the specific K and L which work. So we have to show both that this thing is a common divisor. Show AK plus BL is a common divisor. And then part B is show AK plus BL is the largest among the common divisors. Okay, make sense? So you literally show that it's a common divisor and then it's the largest among all common divisors, and that is what it means to be the GCD. Okay, great. So that is the outline. Let me pause the video and get the board set up because we need some space here. And then we will begin by working through 1, 2, and we'll start 3. And I'll probably have to reset the board again. So let me pause here. Okay, let's start proving this theorem. So I moved the identity down here. A and B are positive integers. This is what we're trying to prove. If you have 2 positive integers, then there must exist some other integers, K and L, for which AK plus BL equals the GCD of A and B. That's pretty interesting. So our proof begins by assuming that we have that A and B are fixed, that they're not moving around, that throughout this problem, they're fixed. We don't know what they are, which is good because we want this proof to apply to any pair. And that's good. We're not going to assume anything about them except that they're fixed. So that's perfectly fine. So we fix A and B, which in turn fixes their GCD. So now it's time for an insight. This is a very important insight. It's an insight that, it's not, sometimes proofs require insights. It's not, sometimes, it's, you follow your nose. You write down what you're given, you apply some definitions, the algebra sort of appears, and you work it out, and those are very good proofs. But other proofs require a little bit more, a dash of additional ingenuity. So Bézout, or I haven't looked into the history, I assume it was Bézout, but often in math, actually things are not named after who, the first person to prove it is not necessarily the person who it's named after, so it may not be Bézout. But whoever it was had an insight, and the insight is this. So consider all possible combinations, AX plus BY, okay? So A and B are fixed, but X and Y are in our variables. So they can move around, and you want to look at all possible values of that. And then among those possible values, actually maybe I'll do an example off to the side. Let's do, I don't know, A equals 6 and B equals 8, I guess. So let's look at all possible values of 6x plus 8y. Okay. So X and Y can be any integers. So if they're both 0, you get 0 out. So 6 times 0 plus 8 times 0 equals 0. Okay, what else can you get? 6 times 1 plus 8 times 1 is 14. 6 times, I don't know, let me just do a couple of -2 maybe. 8 times 3, what would that be? -12, 8, 16, 24, +12. Okay. What else could you get? You could get 6 times, let's do -1 plus 8 times 1. Okay. -6 and 8 makes 2. Okay. What else? I don't know. You could get 6 times -3 plus 8 times -1. So this is 6, 12, 18, -18 and a -8, -26. When I was in high school, I was so good at arithmetic. And then since then, I've just spent 2 decades learning all this math, and now my arithmetic skills have decreased while everything else has gone, hopefully, up. Okay, so here are 1, 2, 3, 4, 5. Can I count? 5 different combinations of x and y. And so you plug in all of it, but they're infinitely many, right? You could have infinitely many options for x, infinitely many options for y. So you have infinitely many combinations of those. And here's what I want to know. The insight is this. Let D be the smallest positive value of ax plus by. The smallest thing that it could be. So in this case, in this list, this isn't positive, right? 0 doesn't count as positive. So 2 would be the smallest positive value in this list. Of course, there are infinitely many other ways to combine it, but actually it turns out that 2 is the minimum. Because the only other option would be 1, right? If you want positive numbers, and these are integers, right? You combine integers, you get another integer. That's what fact 2.1 said. So the only possible other option would be 1, and it just turns out that that's impossible. Because 6x is always going to be even, 8y is always going to be even. You add together 2 even numbers, it's still going to be even, so it's not going to be 1. So, but 2 is possible. See, you can see it right there. That shows it's possible. So for 6 and 8, 2 is going to be the number D that I'm referring to here. The smallest positive value of ax plus by. And then I say, and let k and l be the x and y's that give you that minimum. So in this case, this one works. So our k, if it was 6 and 8, would be -1, and our l would be 1. Okay. Great. So, by the way, it's good practice to, when you're writing L's, L is used as an integer in math, a reasonable amount. I mean, first comes m and n, but L is not uncommon. When you write L's, don't write it like this, because then it looks like 1, right? If you wrote L equals 1, it looked like 1 equals 1. No, make it a little curly, cursive type L. That'll reduce confusion. You also notice that at times in my work, I'll write a 1 like this. That's also, I just sort of, whenever I have a 1 to write, I just sort of, spend half a second and be like, okay, if I go like this, would there be any confusion? And sometimes, yes, sometimes a vertical bar could look like something else. So then I go ahead and write it like this. I don't know. So anyway, that's another point, is 1s and L's and, like the divide symbol. A divides B. The divide symbol also looks very similar. So, in your own work, adopt certain practices to avoid confusion. A 2 could look like a Z. That's why when you write a Z, you should put a little cross in the middle. That'll reduce your confusion. So these are just some pro tips for you. As you become a mathematician, there are certain habits which are just useful and will make things easier for you. Okay, great. So for 6 and 8, the minimum thing you could get would be 2. So D is 2 here, right? From this. So D is the 2, and the K and the L that give it to you are -1 and 1. So that's all I'm saying here. For an arbitrary A and B, we don't know what A and B are, so we can't say it's 2 or something, but it's something, right? And whatever that minimum positive value that you can get That is D. And whatever K and L would give you D, well, those are the K and L. Okay, whatever X and Y gives you D, those are the K and L. Okay, great. So, where am I? So we have D equaling AK plus BL. And now D, K, and L are fixed, right? Because we assumed A and B are fixed. That gives you an actual minimum value, which is D, and K and L produce it. So we now imagine all these things are fixed. They're not variables like X and Y were variables. They're actually fixed numbers. Okay, now what is our goal? This is steps 1 and 2 are actually already done. So now for the big step, the most important step, is step 3. And this is the main goal. I'll write a goal on the board. Goal. The goal from this point on in the proof is to show that D equals the GCD of A and B. Why? Our entire goal was to show that GCD equals AK plus BL for some K and L. We've shown that this D is an AK plus BL. So as long as we show that this D is in fact the GCD of A and B, then we're done. Then we've shown exactly what we want. You could put this in for D and we're done. That's what we wanted to show. But this required an insight because who's to say that this minimum value will be the GCD, right? Someone had to have done a ton of examples or had a very good understanding of this problem in order to realize that the greatest common divisor and the minimum possible combination exactly sort of meet in the middle. So that's cool. So how are we going to prove that D, this minimum value, is in fact the GCD? Well, we're going to do it in 2 parts, as I mentioned in step 1 and step 3. The 2 parts are to show that D is a common divisor. We'll do that one first. And then is in fact the greatest among all common divisors. So part 1 is show that D is a common, abbreviations, divisor in order to make room. So basically what I want to show is I want to show D divides A and D divides B. Now it turns out those 2 parts are almost identical. So I'll just do the D divides A part. Leave it as a little exercise to reproduce the work for D divides B. So how am I going to show that D divides A? How am I going to do it? Well, at this point, I do have this equation, which I have given a star to, because I'm going to use it again. So that's a little spoiler. But how am I going to actually do it? Well, I can't. It's not always the case that one integer divides another integer. However, if you remember from last time, we do have this new tool, which I'm realizing I forgot to write over there. But it's a tool that, any 2 numbers, D might divide A, might not divide A. I mean, it will, but at this point in the proof, we don't know that it does. But if it doesn't divide A, then it gets close. It has some quotient with the remainder. So let's actually use the division algorithm. The division algorithm, which we did last time, which says that any 2 integers, D and A, can be expressed as DQ plus R. DQ, Dairy Queen. Shout out to Dairy Queen. My first job. Dairy Queens are independently owned, and my manager and owner were very hands-off on us, and it was the best job I've ever had. Oh, I love that job so much. So shout out to DQ. Okay, so by the division algorithm, maybe D does divide A, in which case there would be no remainder, R would be equal to 0. But at least we can say this. Right now we can say this. And we can try to then work to the point where we show that R does equal 0. Okay? So that's our goal. Express A as DQ plus R and show that R would be 0, which would mean that D divides A, right? By definition, this would mean, this is the definition of D dividing A. Okay, so A equals DQ plus R. For some integers Q and R. And the thing about R, remember there's that extra thing where R is, it's never less than 0. It's always at least 0. You can't have a negative remainder. And also it's less than D, right? If R were the same size as D or even larger than D, then you could just make the quotient larger to divide out more, essentially. Okay, so we have this. I keep losing my spot. Great, so maybe I'll stop there for this side of the board. And again, our goal is to show that there actually is no remainder. So we're trying to show that R is 0. And to do so, well, what do we have? We have this equation now. And we have this equation right here. So somehow, and we have some extra facts about these things that we've deduced. Somehow we need to combine that to make it work. So let's rewrite what we have. Rewriting A equals DQ plus R. Let's put R on one side of the equation. And A minus DQ on the other. And now let's get rid of the D. How are we going to get rid of the D? Well, we have this equation, this starred equation. D is expressed using A's and B's. So this is a way to get rid of D in our work. So we have A minus D, which is AK plus BL times the Q. So this is by star, the star equation. That's why that's true. It's true according to the star equation. Now it's just algebra. So let's distribute the Q. A minus AK Q plus B LQ. And now let's, we want to write it in the form of AX plus BY. So let's pull an A out of the first two terms. So what would be left? 1 minus KQ plus, oops, typo. This negative should have distributed there. But I do want a plus here. So plus BY, so I'll put the negative inside the parentheses. Okay, there we go. So this is of the form AX plus BY. And X and Y have to be integers. Is this guaranteed to be, are those guaranteed to be integers? Yeah, that's what fact 2.1 said. Any combination of integers, adding, subtracting, multiplying, still going to be an integer. So since 1 minus KQ and negative LQ are integers by fact 2.1, R has been written as AX plus BY. Okay, so so R is one of these AX plus BY things. And that is going to actually, right now, there's enough logic on the board to deduce, enough information to logically deduce that R must be equal to 0. So maybe pause the video and see if you can see why. It's subtle, but see if you can see why R must be equal to 0. Do you have it? It's subtle. So notice two facts. First, D is defined to be the smallest positive value of AX plus BY. So D is the smallest positive value of AX plus BY. It's the smallest thing it can be that's greater than 0. And also note that R is a combination of, so R is one of these ax plus by's and is less than D and bigger than or equal to 0. Do you see? If R were not 0, it would be a smaller positive value of ax plus by. But it can't be, because D is the smallest, right? If D is the smallest, R is even smaller, and R is of this form, ax plus by, the only possible thing is R cannot be positive, it must be 0. So it must be that R equals 0. Do you see? So, so more advanced proofs oftentimes use more complicated logic, where there's an insight, there is, a subtle use of things. These proofs are not, someone did not just sit down and start the proof and just, oh, wait, there, I'm at the end. No, there was a lot of scratch work. A lot of pieces of paper were scribbled on and thrown away and reworked until all these ideas were able to be found and put together neatly. But R is 0, and that's great. Because remember, if R is 0, then A equals DQ, and by the definition of divides, this means that D divides A, which is half of what we wanted to show. Right? We want to show that D was a common divisor, so it divides A and divides B. So that's halfway there. So thus, A equals DQ plus 0, because R is 0. So A equals DQ. So by the definition of divides, which was definition 2.8, we have D divides A. Okay, so that is half of part 1. Proofs get more complicated, but a proof is a combination of big ideas and technical steps along the way. So you have to kind of, have to check the steps, make sure things flow, but also check the big idea. It's a combination of these things. But anyways, we have shown that D divides A. And I would argue that there was really nothing special about A here. You could replace each A with a B, and you'll have, well, okay. It's just slightly different, right? I mean, if you replace B here, you could also write an equation like this. These A's, so that these would turn into B, so the equation would look slightly different, but you would still have this logic go through just fine. So, some very small differences here and there. It would be good exercise for you to then now sit down and write out the proof for the B part to conclude that D divides B. But for the sake of this video, I won't do that. I'll just say, in the same way, in the same way, D divides B. So D is a common divisor of A and B. There you go. So that's the end of the first part, part 1 of step 3 of this proof. Okay, so let me pause the video and I'll get, obviously the whiteboard is full up. If it was in person, oh man, if I were at teaching at Cambridge, one of those old European institutions, probably they have them in the East Coast. I never went to school on the East Coast. They have those whiteboards those blackboard chalkboards that you slide up, so you can have a long proof and it's all visible the whole time. Oh, I would love that. Nevertheless, for this format, this is where I'll have to pause to erase part 1, and that way I can write on the board the proof of part 2, which is to show that D is the largest among all common divisors. Okay, so in part 1, we showed that D is a common divisor. Why is it the greatest? Why can't there be another even greater common divisor? Well, let's suppose that we have another number, d prime, which is a common divisor of a and b. So we have any other common divisor. Why must this one always be less than or equal to d? And I have to say less than or equal to because by the way this has been formulated, there's no guarantee that d prime is not also d. I might have chosen d again. So nevertheless, d prime is some other common, is a common divisor. Just have to be another one. Just a common divisor. We want to show that it's no larger than d. That d really is the greatest possible common divisor. So how are we going to do this? Well, this one is a little bit more follow your nose than the first than the first case. It's complicated, but it's it's less. There's less of a deep insight than in part one. So we have another common divisor. What do we do? In general, you should think about your definitions. Indeed, that's the next step here. Since d prime is a common divisor, a must be equal to d prime times m, and b must be d prime times n. For some integers m and n. Okay, so there you go. D prime is a common divisor. What does that mean? Well, it divides both of them. What does it mean to divide something? It means it's a scaled version of it, just like that. Okay. So maybe I'll say by definition of a common divisor was part of definition 2.12, and definition of divides was back here 2.8. Okay, so common divisor means you divide. What does it mean to divide? It means that. Okay, so then what do? You go back to the one equation that we have. D must be AK plus BL. So start there. It's the one thing we have, AK plus BL. Now you want to say something about how D relates to D prime? Well, now that you have this equation, we can actually do that, right? Because this A relates to D prime, and this B relates to D prime in those ways. So great, D prime M in place of A. D prime n in case of b, in place of b, excuse me. And now if you factor out the d prime, maybe I'll do a d each side. What do we have? mk plus nl. So we have found a way to relate d and d prime to each other. Now, do you see why d prime cannot be any larger than d? If I d, suppose this equaled 2. So if d was d prime times 2, d prime would have to be smaller, half as small, right? If this equaled 3, then d prime would be a third as big as d. So this is why d prime is a scaled up version of d. Because mk plus nl is an integer. There's no way that this thing equals a half, because fact 2.1 tells us that if you combine integers, you get back another integer. Okay, so there are many ways that you could argue this. You could just write it out in words, what I just said. That would probably for your professor be a sufficient explanation. For most audiences, that would be sufficient. You could also do something like this, just to show you one other option. You could say d prime is d divided by mk plus nl. So just divide over that term. And you could just note, hey, d is an integer. The denominator is an integer. I guess d is bigger than 0. Let me write that up. Since this is true and d is bigger than 0, if you have something less than 0, dividing it by 3 actually makes it bigger, closer to 0. But if you have something bigger than 0 that you're dividing by, it makes it smaller. So since d equals this, and d is bigger than 0, and the denominator the denominator is an integer, that tells us that d prime, by dividing out this thing, you're only making it smaller. Or the same size. The bottom could be equal to 1, in which case you're not making it smaller, but you're definitely not increasing it. Either way, so you could use the words that I said, you could use some equation like this. At this point, there's probably some flexibility in what would be considered an acceptable justification for this step. But nevertheless, at this point, or this point, you can conclude with just a little argument that d prime must be less than or equal to d. So d is a common divisor. We proved that in part 1. And if you pick any other common divisor, it's no bigger. So d must be the greatest common divisor. Greatest common divisor, CD. And there you go. That's the end of the proof. So GCD of A and B is equal to D. That's what we just showed in 2 steps, that it's equal to D. And we knew earlier that it was equal to AK plus BL. So the GCD of A and B does indeed equal AK plus BL. That's what we wanted to show in the proof. So we are done. Congratulations, you're still here. I probably some people dropped off, but you're better than them. You stuck through it. You have the grit. You're if you're listening now, this is a good sign about your future. No, I'm just joking. But yeah, go ahead and watch this multiple times if you need to. Go over it carefully on your own. See if you can grasp your hands around a very long and complicated proof. If you're in the book, if you have the book, you can see, Bézout's identity starts here. I have a proof idea section. I have more about the proof idea. I start the proof. It goes all the way over here. So it's long. It's not like a few lines with a few justifications and a little algebra, throw in a definition, and you're good. No, it's long. Anyways, so great. Now, one advantage of having this proven is that Bézout's identity is actually quite useful, surprisingly useful. There are many instances where you might want to say something about the GCD, but you really can't because it's just like this function. But if you can write it in this form, AX plus BL, then suddenly it's much easier to get your hands on and to actually work with and apply in new ways. So next time I'll give you one very short example of that, and I'm just going to give you a proof sketch of it, but maybe that'll be useful for you to see. So come back next time for a short video on applying Bézout's identity.